Good morning. Today let us study about calculation of magnetic moments. How the magnetic moments of coordination complexes are calculated. This is very important. Many questions are asked in JAM and CSIR etc. How the magnetic moments are calculated. It is very simple. There are three formula I have given here. How the magnetic moment is first calculated. We will see the theoretical basis. For example, when an electron revolves around the nucleus, there are two types of motion. Remember, there are two types of motion: orbital motion, and it also spins about its own axis. It also spins like when you throw a ball, it travels in linearly, and also the ball also spins. Similarly, there are two types of motion similar to ball: orbital motion and spinning motion. As a result of orbital motion, orbital magnetic moment is produced. As a result of spinning motion, there is spin angular momentum is produced. Spin angular magnetic moment is produced. Therefore, because of any charged species, electron revolves around the nucleus, will produce magnetic field. Therefore, it will produce magnetic moment. Magnetic field is measured in terms of magnetic moments. They possess magnetic properties. Okay, now there are two magnetic moments. There are two magnetic moment vectors: spin magnetic moment and orbital magnetic moment. These two couple each other. Spin and orbital motion couple each other to form spin orbit coupling, that is called lambda. Okay. Based on lambda, there are three formulas. For example, case 1. In the case 1, lambda is large when the spin orbit coupling is large. See, when the spin orbit coupling is large, the energy difference between the ground state and excited state is very large. Okay. Therefore, this formula, the magnetic moment is calculated by using this formula, mu equal to g square root of j into j plus 1 Bohr magneton, where g is the g factor, LANDE splitting factor for electron, or g factor for electron. Okay, and j is the resultant total angular momentum quantum number. Total, we have seen in RS coupling, LS coupling. Please see the previous videos. Okay, now g equal to 3 by 2 plus s into s plus 1 minus l plus 1 divided by 2j, j plus 1. Now next case is, so using the s, l, j values, we can calculate the g value, and then you can calculate the spin only the magnetic moment of the. This is applicable for lanthanides and heavier elements where the spin orbit coupling is very large. Okay, now when the spin orbit coupling, the spin magnetic moment and orbital magnetic moment coupling is small, and spin orbit coupling is small, then the spin magnetic moment is calculated separately and the orbital magnetic moment is calculated separately, and they are added. Okay, so mu equal to square root of 4s plus 1 plus l plus 1 Bohr magneton, where l is the resultant spin angular momentum quantum number, where l is the resultant orbital angular momentum quantum number. We will see one example and solve your problem. This is due to spin only magnetic moment, and this is due to orbital angular momentum magnetic moment. Okay, in terms of Bohr magneton. In case 3, in few 3D transition metal complexes, ligands quenches or diminishes the orbital motion. What does it mean? For example, when ligand overlaps, binds with the d orbital of metal, the d orbital electron is tightly bound. Therefore, the orbital motion is prevented, stopped, is quenched. Okay, so in certain 3D complexes only, the ligands, due to binding, the orbital motion of the d electron is or quenched or diminished. Okay, therefore this is negligible. Therefore, this formula is derived from this. This is negligible because of orbital motion is removed or quenched by the ligand bonding. Therefore, the spin only magnetic moment can be calculated equal to square root of 4 s plus 1 or mu equal to square root of n into n plus 2, where n is the total number of unpaired electrons. N is the total number of unpaired electrons. Let us now apply to some of the problems asked in GATE, CSIR, JAM. The G values for cerium 3 plus 4f1 and Pr 3 plus 4f2. Cerium 3 plus, what are the G values? Using this formula, we can calculate cerium 3 plus 4f1. Therefore, there are 7 f orbitals. In f orbital, there are 5 d orbitals. Similarly, -3, -2. This is the orbital angular momentum. Quantum number -3, -2. Therefore, S equal to 1 by 2, L equal to 3. Modulus of -3. Modulus. We need to take modulus. Therefore, L equal to 3. For less than half field, this is less than half field. Therefore, less than half field, J equal to L minus S. Remember, for more than half field, suppose more than half field, D8, in the case of D7, half field only, D8 more than half field, in that case, J equal to L plus S formula is used. How the ground state term symbol is determined by using 3 simple rules I have described earlier. Please see that video. Therefore, J equal to L minus S pi by 2. On substituting in this formula, on substituting S value, N value, J value, you will get G equal to 6 by 7. Similarly, for Pr3 plus 4f2 minus 3 minus 2, S equal to 1 by 2 plus 1 by 2. Okay, so S equal to 1 by 2 plus 1 by 2, 1. The resultant spin angular momentum quantum number, and L equal to -3 minus 2 minus 5 modulus. Therefore, L equal to 5. J equal to, for less than half field, therefore L minus S. Therefore, 5 minus 4. On substituting these values in this formula, you will get G equal to 4 by 5. Okay, the second problem asked in IIT JAM is the expected spin only magnetic moment 2.83 for nickel complex. Okay, find the total number of unpaired electrons. Using this formula, we can calculate number of unpaired electrons. So, the spin only magnetic moment equal to n into n plus 2. Therefore, you can use this formula 2.83. In this formula, if you put 2, then you will get this value. If it is 2 something, number of unpaired electrons is 2. If it is 3.83 something, 3 point something, then there are 3 number of unpaired electrons. If it is 4 point something, then there are 4 unpaired electrons, like that. Okay, or you can also in different way you can arrive at. Let us look at the nature of the complex. It is a weak field ligand, therefore it is a tetrahedral complex. What is the formal charge on nickel? Nickel 2 plus. There are 2 ways you can solve. Nickel 2 plus D8. Okay, therefore D8 means in the case of tetrahedral complex, Eg is the ground state. And in the case of octahedral complex, T2G is the ground state. Therefore, on putting 8 electrons, you will get there are 2 unpaired electrons. By following this rule of maximum electricity, there are 2 electrons. Okay, now let us see the third question asked in GATE 2008. The magnetic moment of ruthenium XR core complex corresponds to the presence of how many unpaired electrons are there. As you see in iron, ruthenium, osmium, this is one group. This is one group on 3D series, 4D series. Osmium belongs to 5D series. On moving down the group, the crystal field stabilization energy increases. See, iron, it will be like this. For ruthenium, it will be like this. And osmium, it will be like this. Crystal field stabilization energy increases. Although it is a weak field ligand, here it is high spin. Because why it is high spin? Because it is a weak field ligand. Whereas in 4D 5D series, crystal field stabilization energy is large. This is crystal field stabilization energy delta. This delta is very, very large. Therefore, what will happen? The crystal field stabilization energy is greater than pairing energy. Therefore, you will get 1, 2, 3, 6. Therefore, there are no unpaired electrons. There are 0 unpaired electrons. Okay. So, we will solve few more problems. Remember, these are the 3 formulas. used to answer many questions asked in your competitive examination. Thank you for watching.